Okay, reactions of hydrocarbons. So we have two simple hydrocarbons drawn. The top one is an example of an alkene. It's in fact ethene. And the bottom one is an example of an alkane, in this case ethane. Now they both react. The double bond is much more reactive, however, and the reactions that alkenes undergo are called addition reactions, and they come about because the double bond is very reactive and the double bond springs open, which I'm showing here by covering up one of those, so it's now a single bond, and we've got two things that need to be added on to there, which I'm calling earrings. If you added HBr across to an alkene, then the two earrings would be bromines. If you added iodine to the alkene, you'd end up with the iodines in that spot. And similarly, if you added hydrogen, you'd end up with the corresponding alkane. In this case, ethene would be converted to ethane, but this one needs a catalyst. To add hydrogen across, you need to add a metal like nickel or palladium or platinum. If you look at the position of nickel, palladium and platinum, they're underneath each other in the same group in the transition metals of the periodic table. So that one needs a catalyst. There is one other one that needs a catalyst as well, and that's if you're going to add water across the double bond. So here's our water molecule splitting in two, so we'd end up with the corresponding alcohol, ethanol in this case, and that requires an acid catalyst. So to make the alcohol, we need the acid catalyst. To make the corresponding alkane, we need to add the nickel, palladium or platinum catalyst. All the others just add across without any problem at all, like the bromine water example that you did in your prac work. So if you added chlorine, for example, you would have the chlorine earrings. So we call that 1,2-dichloroethane. So to summarise, the double bond makes that hydrocarbon very reactive, and anything basically adds across it by that double bond springing open and creating two positions to add things across. Now, that reaction is immediate. If you remember back to your prac work, you just had to tap those micro test tubes one or two times, and then you got the bromine water decolorizing, which leads me to your diagram here, that it's always good to make sure that you show people you've done your prac work. So when you add your bromine water to your alkene, they're immiscible because you've got an oily layer. Your bromine water stays on the top. With a few taps, it's going to decolorize, but you're still left with two layers because you've got a water layer and an oily layer. The alkane will also decolorize, but the reaction's slower and it's a different type of reaction. So let's consider that now. So our alkane reacts by substitution. So let's put them up here. So we have to take a hydrogen off the molecule and put something else in it. So for example, if we added bromine water to that alkane, we would need to have ultraviolet light for that to work. We need that boost of energy to enable one of those hydrogens to come off, and we were adding bromine, weren't we? And to be replaced with the bromine. And you must remember to add in your other product, which in this case would be HBr. So substitution reactions happen to alkanes. They're slower, they require ultraviolet light, and remember to make the two products. The idea of substitution is the same as in a football game. So hydrogen came off and got replaced with a bromine, and the hydrogen that came off is now partnering up with the other bromine atom from the molecule. And it is a very good idea. We might just do this one first. Now, it doesn't matter how difficult or how involved the molecule looks like. You just need to remember that the action is only ever at the double bond. So I've created a ridiculous looking molecule here, but all we need to zoom in on is the fact that it is an alkene, so it is going to undergo addition, and the molecule stays exactly the same. The action is only where the double bond is. So, you know, it doesn't matter, you just redraw the molecule to give the product, and that's where the action is with the double bond. All of this stays the same. And for example, if we're going to add bromine water to that, we'd end up with the dibromo product again. And it doesn't matter how ridiculous the molecule is you start with, you just train yourself to look at where that double bond was, and that's where the action is. When you write your equations, you're writing them in full structural formula, as I've been demonstrating in my presentation. Now, you were given a stencil like this, and just to practice those reactions, and we're just going to quickly look at those now. So again, you've got a lot of different molecules drawn, and it doesn't matter how ridiculous they are, you're just going to, the action will be where the double bond is. So in the first case, the double bond is at the end of the molecule, 1, 2, 3, 4, 5, 6, so it's a hexene, 1 hexene. So notice that, and I've just to make the earrings obvious, I've just done them in a different colour. So that end double bond springs open, and that's where the bromines add in. So you're ending up with the dibromo product. The second one, you're adding water across the double bond, and notice that there's a hydrogen ion there because that's our catalyst. So we're going to end up with the corresponding alcohol. And again, that double bond has just sprung open, and the hydrogen and the OH have joined on, addition reaction. Now, the third one is our first example of the slow reaction with an alkane. Notice that UV light is written over the arrow. So, and I've indicated that one of the hydrogen is going off and being replaced with a chlorine, because we've added chlorine to our alkane, and note the other product's HCl, and it's a substitution reaction because it's a reaction of an alkane. Number 4, we've got addition again, because I can see we're adding something to a alkene, and because it's hydrogen, we need to have that catalyst, the platinum or nickel or palladium, and we're just going to spring open the double bond and add the 2 hydrogens in to make the corresponding alkane. Number 5 again, now the action's going to be on carbons 2 and 3, and that's where the bromines sit, because that's where the double bond was. Number 6, we've got the action on the right hand side, that's where our H and Br goes, because that's where the double bond was. Again, in number 7, the molecule is the same as the one before actually, but here our earrings are now the bromines because we've added Br2. Number 8, the molecule's looking ridiculous, but I've redrawn it the same and just sprung the double bond open on the left hand side, which is where those hydrogens will go in the presence of a platinum catalyst. Number 9, drawing the molecule the same. Now the left hand side is where the earrings will go because that's where the double bond was, and we're making the corresponding alcohol. Notice the acid catalyst is added. Number 10, we're adding HF, so when that double bond springs open, that's what we see there as earrings, an F and an H. Number 11, redrawing the molecule exactly as it is, but springing the double bond open and adding a H earring and a Cl earring. No catalyst needed for that one. 12 and 13, notice they're written in molecular formula, so you finish with molecular formula. We're looking at reactions of alkanes and alkenes here, and we don't want to forget the ones we already know. They're complete combustion, so both of them are going to produce carbon dioxide and water and energy, and your really job there is just to balance them. Now, number 14 is an addition reaction. Oh, no, it's not. It's substitution because it's an alkane and there's UV light there. So just one of those hydrogens goes off, replaced with a chlorine, and our other products, HCl. 15, got a fancy looking alkene there, but it's drawn exactly the same. And the middle two carbons has the double bond, and that's what's sprung open to give the chlorine earrings. And a lucky last, we're adding hydrogen across a double bond here with a platinum catalyst, and the hydrogens, once they're across, are not going to look any different to the others, but I've just indicated the two that are actually being added in here are the ones off carbon 2 and 3, because that's where the double bond is. So we're summarising again back to our sheets that we've got alkenes undergo addition reactions very easily by the double bond springing open and providing two spots to stick our earrings, whereas, and that's a very quick reaction, whereas alkanes undergo a slower reaction in the presence of UV light, and we've got substitution there, which means one of them comes off and is replaced with something else. But remember, we were making that other product as well. There's two products with substitution. Hope that helps. Thank you for listening.